first off, so I got some questions in office hours today. I have time for maybe one or two questions answered in class today for people who didn't have a chance to do that. If there's anybody that wants me to answer anything. Yeah.
This is kind of simple, but like, why, if ST equals like the identity matrix, why do you know that both S and T are invertible? Or first, then you then you know that S and T are invertible because like I is invertible or something. This is I just saw it. It basically like since S composed of T equals I, then S and T are invertible.
Because you can write down the inverse, right? So you can define an operator. So what would be if you say ST is equal to I, right? Then you know that. So how would you show that S is? So I guess the idea here is you want to try to show that S is invertible.
I guess both of them are.
And
we have the time. If you base it on question, that's like question 10. Question 9, like, well, ST is invertible and S and T are both invertible. But he's saying, how can you jump from? I think he's saying, how can you jump from that equaling I to knowing that ST? How can you say ST is invertible?
How do you know ST is invertible?
Well, I mean, I was asking if S.
Well, yeah, because if ST is equal to I, the identity matrix is its own inverse, right? I mean, if ST is equal to I, then ST is equal.
Yeah, is it true though that we know that S and T are invertible? Like the individual maps?
If you have a product of matrices being invertible, yeah, because if it wasn't, then the whole thing wouldn't be, right? That's like if either piece failed to be invertible, then
Yes.
then the composition can't be.
Okay.
So it's actually easy to show this by contradiction, right?
Oh, okay. So, okay.
Yeah, like you just say like if suppose T was failed to be invertible, then how could T fail to be invertible? Well, it's either not injective or it's not surjective, right? So, but that means that it's not possible for this statement to hold and also have it be the case that this map, for example, is not injective or surjective, because it would mean that the composition wasn't, if this isn't injective, the composition can't be, right? Any piece of a chain is only, it's like the weakest link sort of idea, right? So like the least regular function in a chain dictates the regularity of the whole thing.
Okay. Could you say if T is not surjective, then the function is not surjective?
Yeah, that's the same.
Okay.
I mean, so like because,
Or, so
well, you got to be a little bit more careful with that. It's like,
usually it's like injectivity.
sure, but if these are operators, then injectivity and surjectivity, like failing one automatically fails the other, right? So if S and T are operators, then you could just say, well, the only way they'd be not the only way they would fail to be injective is if they fail to be, or the only way they would fail to be invertible is if they fail to be injective. And if you don't have injectivity in one of the pieces, you're not going to have injectivity in the whole thing, right? Like that's just, even if this is injective and this isn't, you're still going to have the composition is not injective. That's the easiest, to me anyway, that's the easiest way to see it. Yep.
So for yesterday, we were saying like if lambda is an eigenvalue for T, then T minus lambda I is not injective.
That's right.
So what does that make T? Can T still be injective?
T can be, right? So that's like, yeah, so that doesn't really tell you about T. The only, so like the thing there is you have T. T has some properties. Again, I want you to think of T, like the analogy you should have in your mind is like T is a square matrix. Just an analogy to keep in mind, right? So if you write down TV is equal to lambda v, and that's true for some lambda and some v, then you're saying T minus lambda I v is equal to 0, and that means this function is not injective, right? Because there's a vector that's in its null space that is not the 0 vector, right? If this is true, that means v is in the null space or T minus lambda I, which means that T minus lambda I is not injective. What does that look like for a matrix? Well, does that tell you anything about T, like injectivity or surjectivity of T? And the answer is, well, not really, because this matrix, that's an invertible matrix, right? This matrix is invertible. You could write, I mean, its inverse is, I think, 1, 0, 0, 1/2, right? It's an invertible matrix. Thought of as a map. This map is injective and surjective. So if you had an operation that was TB is equal to 1, 0, 0, 2 times V1, V2, that is an injective and surjective map. But if you took this and you subtracted 1i from it, you get the matrix 0, 0, 0, 1. Well, the fact that this matrix is not invertible doesn't tell you anything about this matrix being invertible, right? So you use this to figure out what the eigenvalues are, but it doesn't tell you anything about the behavior of the original matrix or the original operator that you started with.
Okay, so then the significance of saying like t minus lambda I is not injective rather than like something about t, what's that?
So the idea is you're trying to poke around for special numbers. So like most of the time, this is going to be invertible. But for almost every lambda you put right here, t minus lambda I, if t is invertible, for example, for almost every value of lambda you put in, this is going to be an invertible matrix. I mean, there's a whole lot of numbers, right? And so what you're doing is you're trying to find the special numbers that make this matrix into a that make this operator into a non-invertible operator. There's not very many of them.
A non-invertible operator.
Non-injective. You're trying to find it's like, what is the variable here you should be thinking is you're moving this you're wiggling that lambda value around until you stumble across one that happens to not be injective. And then you save that number because it's special. So almost always, sort of from a mathematics standpoint, almost always, t minus lambda I is injective. When I say almost always, I mean for like an infinity of numbers, that statement is injective. So it's special if t minus lambda I is not injective. In fact, we're going to show that we know the maximum number of these. Right? There's a certain number there's a maximum number of lambdas that make this not injective. So it's special if it's not injective. So you save those numbers. Now, why are they special? They're special because if you can find that, what you're saying is that you have found an invariant subspace of the operator, right? If you find that lambda, you've also found an invariant subspace. You found a vector that you fed into the operator and it comes out pointing in the same direction. And there just can't be that many invariant subspaces, right? There's not that many vectors that you plug in and T leaves them alone except for stretching.
So an eigenvalue would be
An eigenvalue corresponds to an invariant subspace. So eigenvalues correspond to an invariant subspace. Every invariant subspace for T will have this sort of structure, and every vector that looks like this will define an invariant subspace.
What does that say?
Save, I said save these numbers. So we record them, right? When we find one of these lambdas where that thing is an injective, we save it, right? Because every number lambda we find that makes this not injective gives us an invariant subspace. And the idea is I want to chop T apart into small pieces, and the small pieces I'm going to chop it apart into are going to correspond to these invariant subspaces. Yep.
Can you elaborate on that? Like I don't really understand what you mean by those lambda will be invariants of T.
Every lambda you find, if you write down T minus lambda I, it's not injective. If you can find a lambda that makes that not injective, then that means that there's a vector V that makes this true. If that's not injective, then that means the null space of this operator has more than one vector inside of it, not just the zero vector, but more. If this is not injective, then there's a vector V that makes this true. But if there's a vector V that makes this true, then that means that TV is equal to lambda V. And that means the span of V is an invariant subspace for T. And the game is, I want to find the invariant subspaces. This is a way of figuring out what the spaces that T keeps pointing in the same direction.
So is that why V cannot be equal to 0.
Yeah, V can't be equal to 0 because this is a meaningless statement, right? Because I want span of V to be an invariant subspace, and the span of 0 is nothing,
Okay,
right?
thank you.
Yeah. So we eliminate the case where V is equal to 0 because that's always true for 0. Right? T of 0 is always 0. That's not interesting. That's not special at all. It's always true. Okay. Any other questions? Those are good ones. Anything else? Yep.
You went over your office hours a little bit, and like number 6, I think, prove that every degree or function with an odd degree has a real 0. But you assume that function would be odd. It has an odd degree. Is that always the case? Isn't there?
Oh, does it say odd degree and not odd? No. Well, that's okay. I can still use the intermediate value theorem. Okay, so yeah, so what I showed was that if an odd, so okay, so this is my mistake. I showed that if f is odd, then f has a real 0. Okay, so I can use that, and I used it using the intermediate value theorem. Fine. You want to have odd degree instead? All right. The limit as x goes to infinity of f of x is either equal to plus or minus infinity, and likewise the limit as x goes to minus infinity of f of x is minus or plus infinity. And so an odd function eventually, and a polynomial with odd degree, eventually either goes up and down forever on the left and right, or it goes down and then down like this, right? So either odd degree polynomials have this asymptotic behavior, or they have this asymptotic behavior, right? So that means that eventually out there at infinity, there's a positive point and a negative point. So you must pass through 0 somewhere in between by the intermediate value. That's even lamer than the other argument. But yeah, the idea here is that like a polynomial with odd degree has this asymptotic behavior. Right? Eventually it will happen that a polynomial of odd degree has to escape to both positive and negative infinity. And that means it must have a positive value and a negative value. And so somewhere in between, it must have crossed through 0.
For a lot of these questions, is the intermediate value.
Yeah, because the reason that the intermediate value theorem comes up so much is because if you're asked to show that a root exists somewhere, it's really the only tool you've got, right? I mean, unless you're going to use like Descartes' rule of signs or something. Actually, okay, there's the challenge question. Who in here can tell me what Descartes' rule of signs is? Probably you had a 10th or 11th grade. I tutored in high school for a long time, so I know that this is part of the curriculum. Probably you had some teacher somewhere in the ancient past that made you count the number of times that the pluses and minuses changed in a polynomial, right? And that the number of times the sign changed from positive to negative gave you a measure of how many real roots the polynomial had, right? And in some of those cases, it turned out to be that like the polynomial had to have at least one root, okay? But Descartes' rule of signs is too exotic. Like, that's not something we usually use, and it doesn't apply to general functions. But the intermediate value theorem, the reason that works in a case like this is because all I have to show is that somewhere the function was positive and somewhere it was negative. And like, there's really nothing else. Finding roots is actually a very hard problem. Okay, I'm going to point out, like, I know there were a bunch of you guys in office hours. I do want to point out the question. My favorite question was the one about P and P prime having distinct roots. So if P has M distinct roots, I just like this question too much not to give you an idea of how to do it. If P has M distinct roots, then P and P prime share no root in common. I know this is an if and only if, but I'm going to give you the idea works in both directions. I'm going to give you the idea here that the way to do this is to think, well, if P is degree M and has M distinct roots, then it can be written like this. It means that when you factor it all the way down to linear terms, each term only appears twice. but there's not a square anywhere. Each term is to the first power. But none of the R1s, I mean, you could do this with any complex polynomial. Any complex polynomial can be written as a product of linear terms. That's the fundamental theorem of algebra. Okay. And what the roots being distinct means is that none of these repeat. They're all different from each other. Okay. So basically what you're going to do is you're going to rewrite P of Z like this. So I'm going to make this claim. Ri is not a root of P prime of Z. What I mean by that is P prime of Ri is not equal to 0. And the way I'm going to do it is I'm just going to carefully sort P and then take the derivative. Write P of Z as Z minus Ri times Q of Z. I just take out the term I care about, apply all the rest of the terms into the smaller polynomial, Q. What is Q of Ri equal to? If I took Ri and I plug it into Q, what comes out? Not 0. It can't be 0, right? Because there's only one term here that these roots don't repeat each other, and that part of it turns into 0. This is just all these extra terms all multiplied together. Ri does not appear in that list. Q of Ri is not equal to 0. So my claim is take the derivative of P and plug in Ri, and you'll see that you get the answer that you want. And that same trick of sorting P into terms like this, where you've got a polynomial times something else, will also work in the backwards direction. Where the easiest way to do the backwards direction is to assume that P does not have distinct roots. If P does not have distinct roots, so your hint for the other direction of this problem is if the roots of P are not distinct, that means is that one of these terms appears more than once. There's a second power somewhere in one of these in this factoring. Then that means that you could write P of Z as C minus R squared times Q of Z. So if the roots aren't distinct, P can be written this way. Something appears more than once, pile everything else into Q of Z, take the derivative and plug in R. And you'll be able to show that P prime also has a root at R. So there you go, there's some hints. Yep.
Well, when I talk about like R squared, you have to make it explicit that you're not claiming that that R can also be a root of Q and Z.
It could be. Yeah, it could be a root Q of Z. I'm not, it could be, there could be, it could, I mean, the polynomial itself could be Z minus R to the M power, right? It could just be lots of copies of the same root. All I'm trying to do is say some root in that list occurs more than once. Something is a double root when I factor all the way out. And so write it like, you just take 2 of those and write it out. At least 2. It could be 3, it could be 4, I don't know, but at least 2 would be a repeated root. And yeah, in this case, I don't care what Q of Z does. Right? Over here, it matters. Over here, it doesn't. Because I'm just trying to show that when you're all done with this, after you use the product rule, that when you plug R into P prime, if you can probably see the answer. If you take the product rule here, well, the first term is going to have a Z minus R in it. And the second term is going to have a Z minus R squared in it. And if you put R into that, you're going to get 0 plus 0. Okay. That's the idea. Anyway, accusing me of being Axler-like in my arguments. Yep. Okay, so I know I told you earlier that I would try to finish that. I don't think that I have the time to do that right now, but I'd be happy to talk about it afterwards. I just missed one step in that, and that's one where I like. I'm actually going to write that one. I've gotten so many questions on. I'm going to write my own solution to that one, and I'll just post it. I'll make sure that that one's not graded.
Which one was that?
That's the one about show that if ST is equal to TS, ST is equal to TS for all S, if and only if T is a scalar multiple of the identity. It's probably the hardest question on the board assignment. I think it was 16 on 3D. Yeah. So I'll show you guys a solution to that. That's not an easy question. Okay. So remember that lambda is an eigenvalue T if there exists a vector, there exists a v not equal to 0, so that TB is equal to lambda v. So that's what it means to be an eigenvalue. You're an eigenvalue of an operator T if there's a non-zero vector that makes this equation true. V is called an eigenvector for T if lambda is an eigenvalue for T and TB is equal to lambda V. We should say a little bit more though. V is called an eigenvector T for T associated with lambda. So when I talk about an eigenvector, I have to think about it with relation to the eigenvalue it's stuck to. Okay, so eigenvectors come attached to their eigenvalues, which is an important consideration. Eigenvalues come, or eigenvectors never come by themselves. They always come with the eigenvalues that they're attached to. Okay, then he's got some examples in here. Oh, this is cute. Sorry, I said that earlier. Somebody said, why do you call things cute? There's actually right this example. It says, suppose that you have T, which is an element on F2. It's an operator on F2. T is an F2 by T of, which direction does it use? WZ equal to minus ZW. Find all the eigenvalues and eigenvectors. T. So A says, and the eigenvalues, eigenvectors, T if F is equal to R. So if you're in 2 by 2 real space, find the eigenvalues and eigenvectors. So the analysis, we don't really have a lot of tools to work with yet. So let's actually write down what this thing does. So you start with a point WZ, W. And there's Z right there. So you start here at this vector. And then what you end up doing is that turns into minus Z. We should make this more exaggerated so it's clear which direction is which. Okay, so there's this vector, which is WZ. And then T takes that vector and turns it into this one. So what is T doing? How's T transforming the plane here? It looks like a rotation, right? Like it's rotating 90 degrees. Why are we saying degrees? Does he say degrees? Oh, he does. Okay, so we're allowed to say degrees and not radians. All right, so this is sure. Why not? If Axer uses degrees, so this is a 90-degree rotation. Okay, can this map? Can this T have any eigenvalues? But does T send any other vector to 0 besides the 0 vector? So it can't have 0 as an eigenvalue because eigenvalues come with non-zero vectors attached to them, right? Is there any vector in the plane that stays pointing the same direction after T is done with it? If it rotates by 90 degrees, is there any vector that comes out pointing the same direction it went in? And the answer is no. No vector points the same direction. For no vector V has TV in the same direction, as V because it's a pure rotation, right? But if no vector points in the same direction, then no vector can be a scalar multiple of itself. So if we think about the field as R, this map T has no eigenvalues. And if it has no eigenvalues, it has no eigenvectors. So there's an important point to be made here, which is eigenvalues also come from the same field that the vector space is defined over, right? This has no eigenvalues because it turns out that these rotations correspond to complex eigenvalues, and I'm not allowing that. Maybe you guys did it in 206 where you were like, oh, look, by the way, you can factor this characteristic polynomial and I and minus I come out, right? But when we have a real vector space, the eigenvalues must live in the same field. Okay, so this is basically a map that has no eigenvalues. What if I ask the same question, but I ask it about complex? What if I say the same question? Find the eigenvalues, find the eigenstuff of T acting on or in L and C2. Well, just because it doesn't have real eigenvalues and eigenvectors, doesn't mean that the same thing. Doesn't mean that the same thing can't be true, or that we can't have eigenvalues that are complex. How do you find them? In this case, I did nothing. I just like wrote down an analysis and said, oh, look, it's all rotations. And so no directions are preserved. So there's no eigenvectors. What would I do here? What if I actually wanted to find some eigenvalues? Now, what I want you to have in your head is that in the same way, so if I asked you to show that things were linearly dependent, in great big glowing red letters behind your eyeballs, you should see the linear independence equation, right? You see linear independence problem, boom, that equation is going to be on the page somewhere. If anybody ever asks you to find eigenstuff, the very first thing you should do is write down TV is equal to lambda V. Same move, right? You're asked to find eigenthings, write down the eigenvector equation. What would that say in this case? T of WZ, which on the one hand is supposed to be equal to, well, I know what the operation is here, right? Minus ZW. That's what T does. Is supposed to be equal to lambda times WZ. This part of the equation is the eigenvalue equation. This part is just what T does to an input. Does that make sense? So if you're going to be an eigenvalue and an eigenvector of T, you're going to have to satisfy the equation minus CW is equal to lambda WZ. Now what? Yeah. Minus C has to be equal to lambda W. And also, W has to be equal to lambda C. That's a simultaneous system of equations. It's like taught you all that math in the past, and I have to make you use it. I know it's obnoxious. Anyway, if you substitute the second equation into the first, what do you get? Minus Z is equal to lambda squared Z. So minus 1 is equal to lambda squared. So lambda is, did I? No, I did not. I used the zero property of vectors. Thank you very much. Give me minus 10 on my own exam here. What did I do? I wrote 0 as you didn't see it. You didn't see it. I would never, ever, ever, never would I ever divide by a vector. So 0 is equal to lambda squared plus 1 Z. And if I have a scalar times a vector, thanks, Laura, I appreciate it. You're keeping me honest up here. So if I have Z is like, Z has to be non-zero. But just imagine either Z is 0, but if Z was equal to 0, that way it would be W was equal to 0. So that's a no-go. And the other possibility is that lambda squared plus 1 is equal to 0. Lambda is equal Lambda squared is equal to -1. See, it just took a while. I just skipped this part. So lambda is equal to plus or minus the square root of -1. So this has eigenvalues as a complex map. It has eigenvalues. Pure rotations have complex eigenvalues. And then of course, once you know that, then you can go up here and you can actually figure out the relationship between Z and W. If W is equal to lambda Z, if W is equal to lambda Z, then when lambda is equal to I, that means W is equal to IZ, which means your eigenvectors are of the form IZZ. And with lambda, this is an eigenvector. And when lambda is equal to minus I, then that means that W is equal to minus IZ, and that means your eigenvectors are of the form minus IZ. There you go. Yep.
Why IZ common Z is eigenvector, but not W Z?
Well, okay, so remember that like we started with the assumption that like in order to have this equation be true,
Yeah.
right, these relations must hold, right? So these relations have to hold. So how do these relations hold? Well, once I know lambda, that gives me a thing I can substitute in for, I can put an I in here, right? I could either put in I or put in minus I, and that's all I did, right? Am I not doing this right? I mean, aren't the original vectors of the form, it's anything of the form WC that satisfies the equations, but the WZs satisfy this relation for different values of lambda. The two values of lambda it satisfies it for are I and minus I. So with this substitution, WZ becomes IZZ. You can solve it the other way. If you want, you could do minus IW is equal to Z. It's the same vector.
So your eigenvector includes the eigenvalue in it?
In this case, yeah. You have to use the eigenvalue to figure out what the eigenvector had to have been. It could be more complicated than this relationship.
So the WZ is not the eigenvector.
The eigenvector, this is an eigenvector. Any Z that you choose will give you a different eigenvector associated to lambda is equal to I. Every single thing of this form will be an eigenvector. It's all of them.
Okay, but you don't list them twice. You don't list like W, WI.
No, I'm just trying to find like I mean, if I wanted to put like W minus IW instead, that's just a constant multiple of the same thing.
Oh, so that's why you only listed.
Yeah, I just need one. I need one
Okay.
eigenvector, right? I just need, like, I found an eigenvector associated with it.
Okay.
Yes, actually. Implicitly, we're working in the standard basis here. Yeah, now the vector won't change, but its representation will with the different basis for sure. Okay. So here's the major structural result about eigenvectors. Notice that this eigenvector from the picture that we've drawn here, what we're saying is that if you have lambda is equal to I, and just suppose you put Z is equal to 1 in there, then it would have an eigenvector attached with it like I1, right? If I let Z equal 1 here, this is an eigenvector. What are we actually saying when we say that, by the way? What does it mean to say this is an eigenvector? We mean TV is equal to lambda V. Maybe we should check real quick to make sure that we're not just like barking up the wrong tree about how this works. What is T of V? So what I'm saying is T of I1. What is T of I1? What does T do? T takes WZ and turns it into Z minus ZW?
Yeah.
Okay. So T of I1 is the same as minus 1I. Is that right?
Yeah.
Okay. On the other hand, I times I1 is equal to I squared I, which is minus 1I. Oh, okay. So T of the vector is equal to the eigenvalue times the vector. These are equal to each other, which means that TV and lambda V were the same. Evaluating T on the eigenvector got me the same thing as multiplying the eigenvector by a scalar. Okay, it's a verification that this actually is an eigenvector. Now I want you to think about, is there anything that you notice about these vectors? So for lambda is equal to I, we had I1 as an eigenvector. And for lambda is equal to minus I, we had minus I1 as an eigenvector. Anything you can tell me about those vectors? They're kind of conjugate. Are they linearly dependent or linearly independent? Are they? When we're in the complex numbers, are those linearly independent or not? Is one of them a multiple of the other?
No.
Well, it can't be because there's a 1 in this both spots, right? Anything you multiply 1 by out, like you can change the 1, right? These are linearly independent. Which means if I wanted to, I could use these as a basis, right? But yes, an eigenbasis. That's more things in the world of eigen stuff than just eigenvalues and eigenvectors. Right. So these are linearly dependent. And that's actually a major theorem of linear algebra. That's true in general. So here's a big theorem. Suppose T is an operator. Suppose lambda 1 to lambda m are distinct. So by distinct, I mean different, are distinct eigenvalues. And V1 through Vm are corresponding eigenvectors. So the order here matters, right? V1 is attached to lambda 1, and V2 goes with lambda 2 all the way down to Vm as an eigenvector for lambda m. Then V1 up to Vm is linearly independent. Shorthand way of writing this theorem, the statement of this theorem is eigenvectors associated with different eigenvalues are always linearly independent from each other. Eigenvectors associated with distinct eigenvalues are automatically linearly independent. Okay, of course, as a consequence, now I'm going to assign, sorry. Okay, so I want to assign this proof. This proof right here, you should read. And then I want questions. You guys, actually, the last time I gave you a proof 3, people came up with really good questions about it. So I want you to try to look at that argument and see if you understand what's going on. Okay. And the reason I want you to have a chance to do it is because this is going to use the fact that the T's can be applied to these vectors and get lambda V's. It's an illustrative proof. So you should spend the time reading it. This is a good argument. It's not a hard argument, but it's a good one. And then tomorrow we talk about, like, if people have questions about it, I'll go over it. Now, if that's the case, if it's the case that eigenvectors must be linearly independent, they all live inside of a vector space V, that says something about the number of possible eigenvalues I can have. Suppose that the dimension of V is equal to n. And I already know, oh, and let's put T to be a linear operator on V. That statement right there says all of the eigenvectors attached to the distinct eigenvalues should be linearly independent. How many linearly independent vectors can be in V? That's the most, right? There can't be any more than n linearly independent vectors in V because the dimension of V is n. So the longest linearly independent list in V has length n. So what's the most number of eigenvalues that an operator can have? So T can have at most how many distinct eigenvalues? It's got to be n, right? The best you could do, if these were all different and they all come attached with an eigenvector, and those eigenvectors are all linearly independent from each other, you can't have any more than n of them, or there would be a non-linearly independent set. So the fact that that theorem is true is going to force it to be the case that T acting on an n-dimensional space can have no more than n distinct eigenvalues. So there's a natural limit to how many invariant subspaces there are. Make sense? No? Yeah? Okay. This is a super important idea. This is actually the proof of the idea. The proof of this idea is if you're on an n-dimensional space and all of the eigenvectors attached to eigenvalues have to be linearly independent if the eigenvalues are distinct, you can't have any more than n because it would come with a set of more than n linearly independent vectors, which is impossible. So the upshot is
Why do you need to specify the eigenvalues on?
well, because it's going to turn out to be the case. So I'm going to push you. I'm going to see if you remember from 206. In 206, you had this idea that came up about geometric multiplicity versus algebraic multiplicity, and we don't have the characteristic polynomial, but it occurred sometimes to be the case that eigenvalues could be associated with more than one linearly independent eigenvector, right? So it's possible that T could only have, just because if T is acting on R3, like the map we just wrote, right? That T, if we thought about the map T in terms of C, acting on C2, it had two different eigenvalues, right? Did it have to have two different eigenvalues? Well, no, it could have had none, right? That same map thought of as acting on R2 had none eigenvalues. So it could be the case that if you were in R2, you have the full set of two different eigenvalues, or you could have one eigenvalue, or you could have no eigenvalue, right? So the idea is that this gives you the most number of different lambdas that can show up. It doesn't mean that there can't be more linearly dependent eigenvectors running around. Okay. And the fact that they're, I mean, we want to say distinct here because I mean, like, just because you find two different vectors associated with the same lambda does not mean that there aren't more lambdas running around. Okay. All right.
Would all the vectors that you add also be eigenvectors?
No, not necessarily. So one of the big structural results that's a really good question though, because the idea is, if you think about V, and you think about V as being chopped up into pieces, where here's lambda 1, and here's lambda 2, and here's lambda 3, and here's lambda 4, you got some eigenvalues. And living inside of, and these are all linearly dependent, right? So you've got a V1 attached to lambda 1, and a V2 attached to lambda 2, and a V3, and a V4. Each one of these things individually will be a subspace of V because you can take the span of the eigenvector, right? You don't want to extend this to a basis for all of V. What you're hoping is that these guys, which are going to turn out to be called the eigenspaces, is that you can find a basis for each one of these subspaces. So this is a subspace, but maybe it's bigger than the span of V1. That could be expanded. And the hope is that if you take this and expand it to a basis of this space, and this and expand it to a basis of this space, and you do that all the way down the chain, that what you finish with is a basis for all of V. That doesn't always happen. If you remember your linear algebra, one of the big deals about in 206 is when you know that you have enough eigenvectors to make a basis for the whole space. This is like related to change of basis matrix and diagonalization. Like maybe you remember that, maybe you don't. The idea is some matrices could be written as diagonal matrices, right? I have no you have I'm not expecting anybody to just have that on the tip of their brain, right? Like how change of basis and diagonalization works. But the idea is diagonalization in the matrix theory class corresponds to the case when the basis of each one of these subspaces is all together is a basis for everything, right? But it didn't always happen. Sometimes it happens and sometimes it doesn't. Yep. No. Because they could be attached to the same eigenvalue. Right. So for example, the easiest way to see that is to think about this. That's a good question. I'm going to give you a really easy operator. T of V is equal to 1, 0, 0, 1 times C1, C2. So T of V is the identity matrix acting on R2, right? What are the eigenvalues of that? Well, isn't TV equal to 1V for every V? Because it's the identity map, right? Okay, well, that means that T of 1, 0 is equal to 1 times 1, 0. And that means 1, 0 is an eigenvector, right? 1, 0 is an eigenvector of the map because it comes in and comes out pointing the same direction. It's not a very interesting one because it's just multiplied by 1. So T just leaves that vector completely alone. But also, T of 0, 1 is equal to 1 times 0, 1, because that's all T does is it takes the same vector and spits it out. These vectors are linearly independent, but they're associated to the same eigenvector. Okay. Another thing you guys might remember is this situation. What if instead I define a map by TV is equal to 1, 1, 0, 1 V times C1, C2. So there's another map acting on C2 or on R2. Okay. This also has lambda equals 1 as an eigenvalue. But if you remember your language when you learned these matrices, this matrix is so crappy it got the name defective. It's just such a cruddy matrix, right? So this is what's called the defective matrix. And the reason it's defective is because every eigenvector is in the span of the same vector. This only has one linearly independent eigenvector attached to it. It has one eigenvalue and it's 1. But whereas here, you had 2 linearly independent eigenvectors. Here, there's only 1. I don't remember what it is. It's the null space of that, which is anything of the form, maybe 0. It's all like all in the span of 0, 1. Is that right? Yeah, like 0, 1 is an eigenvector, right? But that's it. Every other eigenvector is in the span of this one. So there's only 1 linearly independent eigenvector, as opposed to here where you can find 2. So there's subtlety in here between the number of eigenvalues, the dimension of the space, and the size of the set of eigenvectors that you get out, the linearly independence of the eigenvectors. This is actually one of the core difficulties of linear algebra, is being able to tell, I mean, when you're defective, it's not good enough, man. Right? When you're defective versus when you have a full set of linearly independent eigenvectors. And so you did it before in the language of matrices. We're going to look at it again in the language of generic vector spaces, but it's a central question. When that's true. Okay. So next time what we're going to talk about, is it next time for me to tell you that? It is time for me to tell you that. So next time we're going to talk about what happens with eigenvectors, what happens when we take this machinery and do actually translate it back into the language of matrices, right? So matrices are still going to be involved. We're going to talk about upper triangular matrices and the transformation of eigenvalue and eigenvector information into matrix land. All right. Go ahead, read ahead, read this proof and read the rest of this chapter. And hopefully my voice comes back at some point.